We are back with another further maths tutorial video. Welcome. Today we're looking at something called de Moivre's theorem, and before we continue on any further, I should apologise because I am probably absolutely butchering the pronunciation of that. But I must admit, despite having taught this for a number of years, despite knowing this for many more years, and despite having been taught it many years ago, I'm still not 100% sure about the proper way to pronounce this because I've heard so many other people use so many other different pronunciations to each other. I'm not sure what the true, real one actually is. I've heard people say, like I do, de Moivre's theorem. I've heard people say de Moivre's theorem. I've heard people say de Moivre's theorem. So take your pick, and I apologise if you're cringing inside every time you hear me pronounce it wrong. Luckily, maths, though, is not a speaking exam. Thank goodness. So as long as we can do it, that's good enough. So what is de Moivre's theorem? Well, it sounds mega complicated because it's got that posh name, but actually it's quite a nice, neat result that's quite easy to apply to things. And the first thing I should point out is that it's only for the case where n is an integer. That's what n, that weird e and that weird z means. N is an integer. And if n is an integer, then we can say the following. We can say that cos of theta plus I sine of theta, where I is the square root of -1, the complex number, the imaginary number I should say. If we take that expression in brackets all to the power of n, then we can rewrite this more simply as cos of n lots of theta plus I lots of sine of n lots of theta, which is pretty neat because it means we can conveniently just take a power and then just move it inside the trig function. Worth pointing out, this only works in this very specific arrangement. As you are well aware from maths A level, you're not normally allowed to just take a power of trig and then just move the power as a number inside the trig function, and it's only because we've got this very specific arrangement of cos and sine together with that I that it works this way. But the fact it does is pretty cool, it's pretty neat. Worth mentioning, I'm not going to prove this result in this video, and that's because I'm going to have a video in my Prove It series going through that. Today we're just going to be focusing on some introductory applications of de Moivre's theorem, or de Moivre's theorem, see even I don't pronounce it in a consistent way, and then we shall save that proof for a different video, but also we'll be looking at some more crazy but useful ways this stuff can be used in conjunction with trig in a future video as well, as part of the further maths A-level content. Nice, let's look at an example, and we have to simplify cos 2 theta plus I sine 2 theta times by cos of 9 theta plus I sine of 9 theta, and straight away, for some of you, the temptation will be to just go ahead and multiply out the brackets, but you don't really want to do that. Although it's possible that you will end up with some cosines times by some cosines, some sines times by sines, and some cosines times by sines. That's all going to be a bit of a mess, and although we can use trig identities to then tidy that up, that's a bit of effort. Lucky de Moivre's theorem will help us more neatly tidy this all up. And so therefore the first thing we're going to do is realize that in these two expressions we can move the number that's in front of the theta on the outside as a power. So I'm going to rewrite cos 2 theta as cos theta plus I sine theta all to the power of 2. So the cos 2 theta plus I sine 2 theta has been written like this, and then we can therefore do the same thing with the other expression. That can be rewritten as cos theta plus I sine theta, but this time to the power of 9 because of the 9 as the coefficient inside the trig functions. The reason this is useful is because now we've got two expressions to different powers. It's the same expression though, the same base, and therefore we can use index laws, which allows us to very neatly gather them together as one big expression, one big power, and therefore it's 2 plus 9, which is a power of 11. Nice. And then the final thing we can do is we could also take it one step further. Although we've already done a lot of simplifying by gathering the two different expressions into one, we can now also choose to get rid of the brackets at the end by reusing de Moivre's theorem again. So if we move that power inside the trig functions again to get cos of 11 theta plus I sine of 11 theta. And there you go, we've simplified it. Right, okay, what else can we do? Well, something else you need to be aware of is, first of all, that de Moivre's theorem does still work with negative powers, but it also has a little bit of a quirk in terms of how they sometimes like to write the final answer when minus powers or negative powers are involved. Straight away, the first thing we can do is immediately apply de Moivre's theorem here by absorbing that power of minus 7 inside the trig function. So we're going to have cos of 3 theta times by minus 7, which would be minus 21 theta. And then we can do the same with the other thing. It will be I sine of 3 theta times by minus 7, which is again minus 21 theta. And that is the application of de Moivre's theorem done, but it's worth pointing out that there's sometimes an extra way they like to write the answer, the final answer, when expressions of this type are involved. And to do that, they use a couple of sort of laws to do with symmetry with trig functions. And they are the following facts. The fact that cos of minus theta is equal to just the same as cos theta. And also the fact that sine of minus theta is the same as minus 1 lots of sine of theta. You might be wondering where these expressions come from. Ultimately, it just comes from the symmetry of the trig graphs themselves. But I have actually made, interestingly, a prove it video proving these facts. And so therefore the link on the screen right now will take you to that video in case you're interested in seeing the proof to confirm for fact that those two identities are indeed true. But once we do know them, it does mean we can rewrite the expression we have here, because cos of minus 21 theta can be just rewritten as cos of 21 theta. The minus inside doesn't really affect much with cosine. But then the minus sign inside of the sine theta does affect things a bit more, because it means we then write a minus sign for in front of the sine. So we're going to have minus I sine of positive 21 theta. So just be aware, sometimes they will do this final rewriting step, and sometimes it works in, sometimes you have to do this in reverse. So you'll be given the expression with the minus sign in front of the sine. That's confusing. And therefore you have to work backwards to realize that means you can put minus signs in both the cos and the sine trig functions. Okay then, so putting that into practice in one final, I won't go as far as to call it a mega example because it's still quite chilled to do, but yeah, we have this stuff. So the first thing to be aware of this one is, although we can tell de Moivre's theorem is to do with this stuff, we can't actually apply it yet to either of these two expressions because neither of them are yet in the format we need them to be. So for instance, on the top, we've got a problem because there's that 3 in front of both trig functions that we need to factorize out the front. So we're going to factorize 3, but because it's inside the brackets with the squared, we're factorizing 3 squared out the front, meaning we are left with just cos of 4 theta plus I sine of 4 theta to the power of 2. And then on the bottom, well, we're going to be using that fact we've just looked at in the previous slide, which is that we can realize that this is secretly cos of minus 2 theta plus I sine of minus 2 theta, using those trig symmetry rules we were looking at before. And the reason we've chosen to do this is because it now means we can now use de Moivre's theorem to split up or rewrite the things a bit more. I'm going to rewrite that 3 squared as 9, of course, but then the cos 4 theta plus I sine 4 theta all to the power of 2 can be rewritten as cos theta plus I sine theta to the power of 8. So I'm moving that 4 inside the trig functions and combining that with the power of 2. So giving us that power of 8. And on the bottom, we can rewrite that as cos theta plus I sine theta to the power of minus 2. Nice. Which is good because once again it means we can use index laws. And the weird thing is we're dividing, so that means we've got to take away the power. So it's actually going to be a minus minus situation. 8 minus minus 2 is positive 10. So that means we've got 9 lots of cos theta plus I sine theta to the power of positive 10. Which then means we can do one final step to then rewrite that as 9 lots of cos of 10 theta plus I sine of 10 theta. And okay, admittedly, we could then do another step after that, where we then multiply out the brackets to get 9 cos of 10 theta plus 9I sine of 10 theta. There you go. So those are some basic applications of de Moivre's theorem. Hopefully you found this video interesting and useful, and we're going to be exploring how de Moivre's theorem can be used for other purposes in this chapter in some future videos, so do stay tuned and watch those as well. See you in a future video. Goodbye.